Should actually be recording. Now I'm recording. Okay. And then the line is the line. Okay, so now we can see which one's on the right and which one's on the left. But if you're like, I really don't know, I'm not sure, plug in some points. So this one, maybe we'll plug in y equals 1. We get -3 on the curve when y is equal to 1. Over here, when y is equal to 1, you get x is equal to 1. So 1 is more further to the right than -3. So which one's bigger? The line or the parabola? The line. So even if you don't graph it correctly, or if you have tried to graph and you're just not sure if your graph is right, plug in points to verify that, yes, the thing that I thought was on the right was actually on the right of the graph. So we're going to do line, y. This is not a function, so I have to be in terms of y. So y minus y squared minus 4y dy. So here is where people have done bad algebra. You either didn't distribute the negative or you didn't combine. Well, I don't think it's bad algebra to not combine like terms. It's just like you're doing more work. So you have y and then minus y squared plus 4y once you distribute the negative. You're going to have a fraction over those y's. So like, why not just have one fraction instead and have 5y minus y squared dy. That's just going to make the algebra, once you start plugging things in, these are kind of more likely to be multiple choice questions. So you want to be able to make like the computation down to one answer as simple as possible. So the final answer is 125 over 6. A lot of you did like 125 over 2 minus 125 over 3, which is right. That simplifies to 125 over 6. Or I think I saw some people having 25 over 3 plus 25 over 2, and that also is 125 over 6. So, yay. All right, then we get to number 4. And congratulations, 6th period. I think you are the strongest ones on number 4 of the day. So, yippee for you. So, do you think that it actually matters if you can figure out how to graph this? No. What is relevant? What do you have to know about this function? Tate. Okay, if it crosses the x-axis, in that interval between 0 and 6, is it positive or negative? That's what you need to figure out. So how could I figure out if it's positive or negative? Plug in a point in that interval. Let's plug in 1. When I plug in 1, is it going to be positive or negative? Positive. All of the values between 0 and 6 are positive. Is there any way to make this expression be negative when I'm plugging a positive in the numerator? No, because I have positive and then the denominator is always going to be positive. So we know that this curve is on top and then the x-axis is bottom. If you really care, which you probably don't, but whatever, I don't care. There is no vertical asymptote because if we set the denominator equal to 0, we would have imaginary vertical asymptotes, but it's big bottom, so what kind of horizontal asymptote is it? 0. The y-intercept is 0. This graph looks something like this. Ooh, not that sharp. More like. How cute. So we care about going from 0 to the square root of 6. But again, if you couldn't figure out that graph, don't get stuck with the graphing. Just plug in, figure out if it's positive or negative. All right, so we're integrating from 0 to square root of 6 of x over x squared plus 2 dx. What integration technique do we need to do? U sub. Some of our friends are actually writing this down, which I feel like is smart. If I didn't know how to do this problem, I would probably be writing it down too. Just a crazy idea. So if I'm trying to now solve for dx, dx is equal to du over 2x. This is from the 1988 FRQ 5, if you didn't read it. The one from our classwork last class was, I think, from like the 2003 FRQ 5, number 7 on the classwork. So kind of like it comes up fairly frequently for them to divide a region into some unknown K, like with X equals K or Y equals K or something like that. So you're going to start noticing that you're going to do U sub a lot now, because like congratulations, you've elevated to the next level of calculus. And I'm probably at this step just going to go like this and cancel out my x's and not do the full U sub thing. But you're just babies, I guess, at this point, so I'll fully U sub. But if you see me canceling out in this step, that is what I am mentally doing. I'm canceling out the x's there. All right, so then we got 1/2 1 over u du. We're going to integrate this today in class, and you're going to fumble with it. I want to talk about integrating 1 over u du. If I rewrote this and used the second fundamental theorem of calculus, which is adding 1 to the exponent and dividing by it, when I add 1 to the exponent, what happens? What's the exponent become? 0. So if u to the 0, and I divide by 0, am I allowed to divide by 0? No. So we're like, uh-oh. That's when ln comes in place. So if you have a divide by 0 when you've integrated it, you need a trick. So that's why it's ln u. It's because it's like, hey, we're alleviating this issue. All right, so spoiler alert, this becomes ln u. Absolute value, because logs have to be positive. So if ln, absolute value, u is x squared plus 2, not the entire expression, from 0 to square root of 6. A lot of you left your answer as 1/2 ln 8 minus ln 2. There's nothing wrong with leaving your answer like that. But when we go to part B, you need to take that area and divide it in half. If I see a log minus log or log plus log, my life is going to be a lot easier if I can get it to a single log, if I have to use it for something else. And I'm going to be using this area in part B, so I want to make it one term. So I have log 8 minus log 2. What can I do? Yes, I can divide them. A minus sign is like between logs is fancy division. You can leave it like that, but there's a 2 multiplying the front of it. What do we do, or a half, I mean. What do we do with the half? Yes, it's the exponent. So now we have ln 4 to the 1/2, which is really like the square root of 4. What's the square root of 4? 2. So again, totally fine for you to leave it as 1/2 ln 8 minus 1/2 ln 2, but because I'm trying to do a lot of algebra with it in B, I don't want to deal with all that if I can deal with ln 2. Okay, so then we know this whole region is ln 2. Then we're taking some vertical line and cutting this region. We want to figure out where do we cut it so that they are 2 equal parts. So if the whole region is ln 2, what do each of these parts have to be? Half ln 2. Some of you did like where you integrated from 0 to k and set it equal to k, integral from k to square root of 6 of that region. Again, that would work. It's just like computationally rigorous versus going 0 to square root of 6, x over x squared plus 2 dx, equaling half ln 2. There's just like way less places for you to mess up if you just did it with the half ln 2. Okay, and we already know how to integrate this because we just did it. Oops, sorry, 0 to k, not square root of 6. Two. All right, I'm going to get rid of the half just because, like, why not? And here's another thing I saw people doing, which I was like, great, you have a good instinct, but you're not doing the algebra pre-calculus correctly. At this step, if I had raised both if I exponentiate, so do e, I'm raising this entire thing to the exponent of e. And this entire thing to the exponent of e. So like, you can't cancel out these logs right here. And I can't e everything. When you're exponentiating, you have to do like one side is the exponent for the base, and then the other side is the exponent for the base. So you need to get those logs to be one term. So, or maybe a smart idea, maybe add the ln2 to the other side. I didn't think about that until last period when someone said, what if we added ln2 on both sides? And now we have 2 ln2. Ooh, that's cute. A little bit less division happening. At this step, I also can't get rid of the log on the right-hand side because there is a 2 in front of the log. The log needs to be a single log with nothing multiplying it and nothing adding it. So how am I going to get this 2 not there? Made it get the exponent. So make it be a 4. Okay, now I can e everything. Because I have single log on left, single log on right. Now the logs will cancel out. K equals plus or minus the square root 2. Is it both of the answers? Yes or no?
No.
Why no?
Because it's only talking about 0 root 6.
Yeah, so really the K we want is square root 2 because of our boundary. Whew, that was a good one. We had to dust the cobwebs off of our calculus real hard. Okay, today we are gonna be doing a little bit of physics. Let's get going. The applications. And just so that you understand my thought process, because someone in 4th period questioned me, which is fair, you can question me. My idea here is that last class we did something you've done before. This class, we are doing something new. So that by next class, when we're doing something you've done before, you can like marinate on the new work stuff and like let that mush around and cook a little bit in your brain while you're like, oh, volume of cross section. I did a whole project on that. And then the next class after that, you do a little bit more new things. And then you're like, oh, volume of revolutions. Right, I did that. Okay, I had a whole AP exam question on that. And then we do a new thing. And then the next class you're like, well, we practice. And then the next class you're like, average values, integral over interval. Right, that's so easy. Okay. So that's why we're breaking up. And I think since it's new and I think work is kind of trickier for some people, we break it up into multiple parts so that you have more processing time allowed for you. Okay, 1.5a. The lag is crazy. Okay, so this is an introduction to work problems. And I'll get my little microphone on. The AP Calc course doesn't have topic 1.5, but this is something that is found in every Calc 2 class and Physics 2 in college. So a college Physics 2 class is an AP Physics C. So Physics C is physics with calculus. So the reason I love this because I want you to like go into other math class or engineering or whatever classes you go into and not feel completely inept. Like I've never seen this before in my life. But also, why do math if you're not going to understand like how it's used ever? So a lot of the math that we're doing is super useful, but you just have to like have learned the applications of the math that you're doing. And another reason I love this is for anyone who has taken Physics 1 or is currently taking Physics 1, you know that in physics, there's a lot of like random formulas you just kind of have to like memorize. I hope that after I teach you some of this stuff, you will actually understand where those formulas come from. In Physics 1, you don't have to have calculus. It's algebra-based physics, so you just memorize all these formulas, and you're like, huh, what? The formulas are are calculus. They're from like integration mostly, so or derivatives, I guess, like particle motion stuff, you know. But I think that this will help physics be a little bit more like, oh wow, the physics is physicsing. If you're in it this year, if you've taken it before, sorry, but yeah, too late for you. But maybe you're in an upper level physics, I guess. So work. The concept of work is super important to scientists and engineers. My sister is a mechanical engineer and also a super big nerdly mechanical engineer. And she uses work and hydrostatic force literally like every day on her job. And she does Taylor series often on her job too. So big nerd, but physics and engineers, or scientists and engineers and physicists use work. So work is basically the energy something needs to do its job. So if we think about some applications of physics, a crane lifting something, a spring being depressed or stretched, a rocket going into outer space, a plane taking off too, a truck pulling something along the highway, all of that requires energy. All of that is, we can calculate the work required to do those things. Work is done by a force when it moves an object. So if the force applied to the object is constant, work is very easy to calculate. So the work, when a force is constant, is just the force times the distance. I prefer to say force times displacement, and that might be the calculus in me, but distance and displacement are different. So force times displacement would be like where I started and where I ended up. How much did I get displaced? That's the D that I care about. So the amount of, the many types of forces, we could have gravitational force, electromotive force, centrifugal force, so on and so forth. So force can be thought of as a push or a pull. So you might be moving something from like a state of rest to a state of motion. So right now, this object is a 50-pound object, and its force is constantly going to be 50 pounds. And we're displacing it 4 feet. It could be 4 feet high. It really probably should have been a horizontal picture, but we're just displacing it 4 feet. One thing I want to talk to you about is that pounds, anything that says weight, a pound is already, pounds are already a force. So if you're in the units pounds and feet, if you see pounds, it's already a force. Probably those of you who have taken physics are familiar with having to make a mass into a force. So in physics, they usually do standard units. So that would be like kilograms. And you have to take kilograms and make it into a force by multiplying it by the force of gravity. So if you're in the units of kilograms, this is a mass, not a force. So kilograms is a mass. It needs gravity to be a force. So the units for, if we're in force, are kilograms, which is your mass. Here, actually, let's do that backwards. Let's do mass times gravity. This one's units are in kilograms, and gravity's units are in meters per second squared. So when you have kilograms times meters per second squared, you actually get newtons. And if we're doing work, just while we're talking about units, work is force times displacement. So you're going to have the units being newtons times meters, which is actually called joules. 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 fun facts for your life. Okay, that's all about like kilograms. So if we're dealing with kilograms and meters, which I think one of our classwork problems, we're going to deal with that. Please note that it's in meters. This is a meter, not a mass. This is a meter. So if you're given something in centimeters, you have to change it to meters to be able to get it to be a joule. So it must be in meters when you're doing work with these units. That's kind of why I do it in pounds, because it's not as much conversion, and I'll save that for Ms. Waugh to deal with for you. So we're just doing work of lifting something and moving it a distance. So this force is constant. Work is force times, let's do this, times displacement. Or distance. I like displacement. So the force is 50 pounds, and we've displaced it 4 feet. What's 50 times 4? 200. These units are in foot-pounds. Please notice, it is not foot per pound, it is foot dash pound. A lot of people today have been putting like the division sign. It's not a per situation, it's just like feet times pounds, so it's a foot pound.
You call that like pound feet, like pound feet of torque in a car? That'd be a way to say it?
Yes. Okay, so then when we do work with a variable force, most work is going to be variable, or most forces, are going to be variable. If we integrated this force, you're going to have force times x from A to B, which really gives us force. I don't know why I'm doing it in highlighter. Hang on. Force times x from A to B, and which gives you force times B minus A. What is B minus A essentially? Displacement or distance, yeah. It's almost like what we've been doing. It's not that much more complicated. It's only like a lot of forces, if you think about like an airplane taking off. It takes a lot of force to get it off the ground, but then the force kind of peters off like once it's up in the air. That's a varying force. So that would need an integral, because you have some kind of like, if this is my force equation, and doing something like this, I can find the force at just one spot, but I'm trying to get the work, I'm trying to accumulate like all of those forces. So I'm adding up all the forces over time to get the total work, the total energy that I need. Okay, so we're gonna look at generally 2 types of work problems. Today, we're doing everything in the first column. So we're compressing springs. We just push something, that's just like F times D. We're gonna put something into outer space, and we're gonna talk about gas. Then in 2 classes, we're gonna be raising stuff with chains, and in 4 classes, we're gonna be pumping liquid out of tanks. So here, let's do Hooke's law, which is springs. Look at Hooke, he's so fabuloso. Look at those sleeves. Wow, he's just so cute. So Hooke came up with a way to calculate how a spring is being compressed or how a spring is being stretched. So the force has some kind of elastic limit, but he realized that it's proportional to the distance. The force is proportional to the distance x. So whenever you see something that's like talking about proportionality, you need to have a constant of proportionality. So K is that constant of proportionality. So K is our constant of proportionality, aka the spring constant. And X is the distance the spring has been stretched or compressed from its original length. I'm going to refer to the original length mostly as the natural length. So if we think about a spring, I really should have brought my son's slinky in. But if we think about a spring and you like hold a spring up in the air, it's not completely compressed, right? Like think about a slinky. It's going to be sort of like hanging and loosely stretched out. Where, if I keep holding it steady, where it ends up at the bottom is its natural length. So that's just like how the force of gravity has pulled it down this far and it's just hanging here. And then how much we displace it, compress it, or stretch it from that natural length is going to be like the x, how much it's changing. Okay, so looking at example 2, we have a force of 50 pounds compresses a spring 5 inches from its natural length. So it's compressed 5 inches from its natural length. So x is going to be 5 here. So it doesn't matter that it gets compressed to 15 inches. It's how much it changed its displacement from its natural length. And this is its force. So we're going to find the work to that helps us calculate our spring constant. And then we're going to find the work to actually compress it those 5 inches and then compress it 5 more inches after that. Okay, so we got our force. Our force is 50 pounds. And our displacement is x. It's from the natural length is really important. So displaced 5 inches from the natural length. What is K? 10. So that means our force equation is 10x. I guess K is 10 pounds per inch, if we're being specific. Okay, so the work is accumulating all those forces we had to apply in the first 5 inches. So work is equal to the integral of force dx. Because again, that's like going to be the force times the displacement at the end. So in this case, our force equation was 10x. So we're integrating 10x dx. What is the work to compress it 5 inches? Really from its natural length. So 0, even though its natural length was 20, there was 0 work happening to get it to 20. So this is it where when it's hanging at its natural length. And what do you think the top boundary should be? 5. 5 is the displacement from its natural length. All right, integrate. You get 5x squared from 0 to 5. 5 cubed, essentially. And we're in inch pounds. Now, on C, it's already compressed that initial first 5 inches, and we want to figure out the work to compress it 5 more inches. So try to set up the integral for that one. We're not saying it's compressing from its natural length. We've compressed 5 inches, now we're compressing 5 more inches. It's the same force equation because that's this spring's forcing equation. So once you figure out the force equation in like whatever scenario you're in, that's the force equation the whole time. All right, so we're starting at 5, and where are we going to? 10. I should put my that was easy button up here. Okay, hopefully on example 3, you kind of feel like you'll get why we have to integrate this a little bit more. We're pushing a chair that's on casters, and casters are these things you can put objects on that help them move. On a floor with, do you have a question?
Yeah.
Yes?
Wouldn't X be different though, if you add an extra 5 inches, so force would be 5x, no? Because X
Mm-mm.
no, it doesn't.
No, it's just that's the displacement that you're moving. The force on this whole system is 10x. And then I'm like adding up the forces from 5 to 10. The boundaries is the extra 5 inches.
Okay.
Like this, like whatever to, when you get that initial 50 pounds to compress it 5 inches, you have figured out the forcing equation for this specific spring. Okay, so we have this chair, and I'm pretty sure they just waxed the floor here because then they had to like really push it to move it anywhere, and then all of a sudden now it's easier to move. So we are now going to draw, we're going to try to find the force at exactly 4. So draw a vertical strip at 4, and the scaling is crazy. This is 4 down here. So we're really trying to find just this little bit of force. Over a displacement of 0.2. Okay, so then we're just doing, first we have to find the force of moving the chair at 4. So this is kind of reminding me of related rates. So this is the force just at the moment when x is equal to 4. We're just plugging in 4. So that's 80 e to the negative 8 over 5. Which, if we had a calculator, beep boop, beep boop, boop, 16.152 pounds. So this is the force of just this one moving the chair at 4 feet. Then the work at the moment is equal to a constant. This force at 4 feet is a constant number because we're just finding out this one little instant. So it's just going to be force times displacement because we're not trying to figure out the work for the first 4 feet. We're just finding the work at 4 feet. Our displacement was 0.2. That's what that change in x is for. That's the work just in this one little strip. That's how much energy at x equals 4. If we want to find how much work to move the chair the first 8 feet, now we're going to have a bunch of little strips that we have to add together to get to 8 feet. So each of those little strips is the force. So we're going to add them together, or each of those little strips, when we do times the displacement, is going to be the work. So it's like add together all those works. What's a better way to do something than adding? Integrating. So we're going to integrate the force, which they gave us. What are the boundaries going to be for the first 8 feet? Jackson, what do you think? Mm-hmm. So where are we starting?
0 to 8.
Uh-huh. So we're going 0 to 8. Phew.
You just like worded it like a trick question.
Did I? Oh, I'm so sorry. I wasn't trying to make it a trick question. So if we integrated this by hand, we would have to know unit 2. So to integrate by hand, would require integration by parts. Which we'll learn at the beginning of unit 2. Instead, use your calculator. But I'll do it for you. Beep, boop, beep, boop, boop. About 103.6 foot-pounds. All of the work problems are going to be calculated. Like if I give you a quiz or a test on this, it's going to be calculator allowed. Try to set up what you would do to move it infinity feet. And do you think it would actually make sense? Let's look. What would the boundaries be to move it the first infinity feet? 0 to infinity. So moving something infinity feet. This function is exponential. It has a horizontal asymptote that it is approaching. When we approach a horizontal asymptote, these little strips are going to get smaller and smaller and smaller. So we're going to be accumulating really close to 0. This converges. So because it converges, you can integrate to infinity and get a number. Because it's converging to basically adding on zeros at the end. It's just like keeps adding on 0, adding on 0.00005. And the next force would be 0.0000008. So you can approximate the work of something that converges. If this was something that went like, woo, and then like was going up forever, that would be what's called diverging, because it's going off, and this area would just keep getting bigger and bigger and bigger, and you would not be able to approximate it because it would be infinity. But something that converges, you can approximate. So this, with an infinity, is also unit 2. This is called an improper integral. Luckily for you, the Desmos calculator can integrate infinity. The TI-84 doesn't have, and the Inspire doesn't have an infinity button, but Desmos does. You can just type INFTY and it'll get it for you, which is so cutesy. If it's something that's converging. If it diverges, it won't do it for you. Little heart eyes on Desmos because we love Desmos. It's just built different. Okay, so now, second to last thing, I think. Newton's law of universal gravity. This is the portion of the law that we're going to care about. Just so you know, I don't expect you to have all of these memorized. I'm either going to give them to you, but this description also tells you this equation. So like the weight and the force varies inversely with the square of the distance. So the weight and force, here let's do highlighter. The weight is the force. When it says, the second it says varies, you need to have a constant of like variability, I guess would be the word I'm looking for. Inversely means division sign. And then the square of the distance is going to be the x squared. That's like algebra 2. Like varies directly or proportionally is multiplication, and then inversely is division. So this gravity is basically what we're using to figure out how to launch a satellite into space. Yay, Sir Isaac Newton. Interesting helpful things to know is that the radius of the Earth is 6,400 kilograms, or about 4,000 miles. You're about to see how bad I am with saying decimal places, so bear with me while I struggle to say 1,000 versus 100. Okay, you would think as a math teacher I'd be good at that, but no. So we're launching a satellite into orbit. The weight of the body varies inversely with the square of the distance from the center of the Earth. So like this whole force equation is based off of its distance from the center of the Earth, which is why this is going to make it like more complicated. So the space satellite weighs 1,000 pounds on the surface of the Earth. So where is this satellite from the center of the Earth? How many miles from the center of the Earth is it? 4,000. So assuming the radius of the Earth is 4,000 miles, now we can figure out the force equation for this satellite. So this satellite weighs 1,000 pounds. A different satellite might weigh 2,000 pounds. It might weigh, I don't know, something else. But this specific satellite is 1,000 pounds. So this is the force equation. We're going to get the force equation for this specific satellite. So the pounds, are pounds already a force? Yes, so this is a force. And then the radius is the displacement that this satellite is from where we need it to be. So we're going to have 1,000 equals c over 4,000 squared. Do we get why I plugged in what I plugged in? So this is going to give us the force for the whole, this is the force equation for every part of this question. When we do whatever work we're doing is going to involve this force equation. So we get C is equal to 16 billion with a B. I think billion, right? 1,000, yeah, billion. Which is, so that we don't have to write that, ain't nobody got time to write all those zeros every time. 1.6 times 10 to the 10. So our force equation is 1.6 times 10 to the 10 over x squared. This is the force equation for this specific satellite. So every single part of this question, you can already, if we're doing work, we're going to be integrating that equation every single time. It's not changing. Because this satellite weighs that much on the surface of the Earth. Okay, so write and evaluate an expression that represents the amount of work to propel the satellite from the surface of the Earth to a height of 12,000 miles from the surface of the Earth. So we're doing work. We already know we're integrating 1.6 times 10 to the 10 over x squared dx. This force equation is based off of where the satellite was relative to the center of the Earth, not the surface of the Earth. That 4,000 feet was where it was relative to the center of the Earth. So where did the satellite start relative to the center of the Earth? 4,000, I think I keep saying feet, miles. 4,000 miles from the center of the Earth. The satellite starts already 4,000 miles from the center of the Earth. And then it's shooting 12,000 miles off of the surface of the Earth. So how far from the center of the Earth did the satellite actually go? 16,000 miles. So we're figuring out how much work is required to get this satellite from the surface of the Earth, 4,000 miles from the center, into space, 12,000 miles from the surface, which is 16,000 miles from the center of the Earth. All right, and then beep, boop, beep, beep, beep. 3 million mile-pounds of work is required to shoot that big old hefty satellite into Earth. Which might be why it's so expensive to put things into outer space, plus like labor and like materials also, like brain power costs money too. Okay, so that's just like the fuel-ish calculations. Now we are going to go, all right, I need to help you with the wording of this. I probably need to reword this C. How much work is required to lift the satellite an addition, like 60,000 miles from the surface of Earth from its like current position? The position in part B is what I'm talking about. Try to think about what the boundaries need to be. So if it's going from its current position in space, let's look at B. Really, we're saying we're here, 16,000 miles. We want to go from the surface of the Earth to 60,000 miles. The displacement between those two is like 48, whatever, something like that. But, what should my lower boundary be if I'm saying from its current position? 16,000. And what's my upper boundary going to be? 64,000. Because 60,000 is from the surface of the Earth, and we're going 64,000. So we're adding that 4,000 to the 60,000 because we have to figure out its distance from the center of the Earth. And this is where the satellite is now. All right, we get 750,000, not too bad, miles, because that's only like a little bit of a distance change. And once we're that far away from the gravitational force of Earth, work gets a little bit easier. The next part of the question is asking you to figure out what % of the total work necessary to propel the satellite to that height is done in this part. So the proportion would be what we currently figured out in this part, plus the total amount of work. So there was work, this portion that we just found really was here. So part C, we actually figured out the work to go that distance between 12,000 miles off the Earth's surface to 60,000 miles off of the Earth's surface. But we had to figure out the work to propel this whole distance. So what percentage of the work was C total? To get it that far, we have to take what we found in part B, 3 million, plus, I was going to say billion, plus our current distance now. So this is what part B, to get to 16,000 from the center of Earth, plus the additional, whatever that distance was. Fun fact, this gets you to 0.2, which would be 20% of the work. So most of the work to get the satellite to go into space, 80% of the work happened in the first 12,000 miles from the center of the Earth. 20% of the work happened in that last 48,000 miles. Okay, last thing. We can do D, but we're running out of time. So let's do Boyle's law. Let's look at Boyle. He doesn't have as cool of sleeves, so disappointing, Boyle. Boyle is dealing with pressure. The first part is kind of like not super relevant, but we'll read it. The picture, and the pressure of gas is inversely proportional to volume. So pressure equals constant of variation. Inversely means fraction, and the volume goes in the bottom. So the picture on the left, the temperature is 300 of the gas is 300 degrees Fahrenheit. When the pressure is 1, the volume is 4. When the pressure is 2, the volume is 2, so that the constant is 4. That doesn't help us figure out what's happening in the second picture. So that's why I read that so fast. The second picture, the handle has moved vertically, thus work was done. A quantity of gas with an initial volume of 2 cubic feet and a pressure of 400 pounds per foot expands to a volume of 4 cubic feet. So that's the part we need. We have the pressure and the volume. 400 pounds per square foot of pressure equals K over 2 cubic feet. What's K equal? 800. So our pressure equation, pressure is also a force. Our pressure equation is 800 over V. So what is the work done if the gas is expanding from 2 to 4? What do we think we need to do? What are the boundaries going to be? 2 and 4. All right, we talked about this earlier for a reason. What's the integral of 1 over V dV? Ln V. (800) ln 4 minus ln 2, which is really 800 ln 2. I'm not going to bring that 2 to the 800th power. It's crazy. It's about beep, boop, beep, boop, boop. That's my calculator noise in case you didn't figure that out yet. Okay, how much time? Oh, we got so much time. How fun. We're going to be doing 1, 4, and 5, and before I forget and you start working on it, for classwork number 5 is in centimeters. You need to go convert to meters because your force needs to be kilograms times meters to be newtons. So we need meters. And then the integral of force is equal to joules. When we go N times meters is equal to joules. Fun facts for your life. That's for number 5. Okay, so we're doing 1, 4, 5. 1, 4, 5. There's this weird little staple happening on the paper, you might notice. And that weird staple is there because I don't actually care that these papers stay together. The first page is your classwork. What do you think the second page is? Your homework. Ooh, and we're doing all of the homework. This is the type of thing you need to practice. All 7 questions of them. We're doing 1, 4, and 5. It's called a stapleless staple.
Do a very good job.
I know, that's why I was saying I use stapleless staples for things I don't care stay together. Environmentally friendly though. It's more just for me to pass it out once instead of having classwork, homework. Very cutesy. Here or further?
I like English as a
Oh, wait. Okay, I was gonna say, so do you want to wait? Oh, wait, no, that's
So it's basically like this. So F 46360 is yeah, K 10. Yeah, this is and then K 36.
Wait, am I right? Oh, yeah.
Hey everybody, what's the equation for work? So, is time involved in that? No, so same amount of work no matter how fast or slow the squirrel is climbing. True.
Yawn is not related. Right. So we know 4 equals 10. Okay, so distance equals 4.
I should have let you struggle.
How much work is done then? So
Oh my gosh. See, this is why we have beef, it's because you're so dramatic. You said I was gonna push and shove you? Have I ever pushed or shoved you? Oh my gosh. I think that's called definition of character.
Exactly. This is my point right here.
Yeah, definition
You say
of my
things like
character.
that. I think so.
Oh, yes.
I thought you said development of character, and I was like,
You were saying I push and shove you, I said that's
defamation. I think you said that would be development of my character.
Well, that too, but no, defamation of my character.
It's
It's just work, but it's like, it's just like give you like relative force to Reese over here, oh my god, I can't get it to Reese.
do we all agree 50 pounds?
Yes, and I have WD-40. Okay, WD-40, all the force to get ready to see again. We didn't know if we're gonna do this one. With how like not erasing it's.
okay. Now what's the last one? 5?
Yes.
Okay. You don't need to tell Ben that.
What did you say?
No, Alex
So let's find, so, you want to pass it in X, so.
Hi, Ben. I haven't seen you in so long.
I'll tell you, I'm super excited to quiz now.
Yes, it's very exciting.
Are you gonna be working on that?
Yeah, hopefully. I'll let you know. Oh, yeah, yeah.
That you and me.
So, a centimeter times 20 centimeters is 0.2 meters. 25 is 5 meters, and then 30 is.
Centimeters are this big. Yeah, that's right.
Times 100.
Times 30.
Do you believe me or no? I can ask this question if you don't believe me.
Let's go do your work.
I'm
Yeah.
centimeters to meters is centimeters times 100 is a meter, right?
Yeah, so take the centimeter and divide it.
That's what I said. Take a centimeter. What?
You divide.
Centimeter by 100.
Because you do a centimeter. Yeah.
No, but a centimeter is this large.
Yeah.
Times 100 is this large.
There are 100 centimeters in a meter. But to go from 25 centimeters, how much of a meter? Yeah.
I'm going insane.
We are. I believe.
Yes, I
It was never not like, even if I didn't write I got this.
Okay, so I need to
Yeah, I turned those into meters like you said.
So I'm
That was easy though.
And then you have to figure out.
I'm gonna look this up, but I don't have my phone right now. It's
Okay.
Let's lock it.
We got 7 minutes. So let's go.
Is that right? Well, also, there's a
We're actually burning base. Number 5.
We gotta put it in.
Oh,
That's not 20, 25,
I don't know.
If you were to be like new
Oh, okay.
The left is not.
Yeah,
31.25. 45 years times 25.
Wait, is there something else like I'm really, I feel like it's really more than one. All these places like.
How did you get it?
Okay, that's 50?
Yeah, exactly.
Alright, what do we do after?
This is me.
Oh, that's my
That's
Oh, okay. That's a,
0.0. That's what we 20, 25.
and that's 26.
Yeah.
Wait,
And then
Integrated 250 over 2 is 125.
5 centimeters. 0.5.
Oh.
But then we get 25 to 20.
So,
Okay.
with the force of whatever natural how far did it get?
And then,
I know like 45.
That's crazy.
Can I see real quick?
So what did you take instead?
well, no, is it even?
Oh, it's not. It's
Okay, guys, wait, this sounds right. Can I see board real quick? Thank you.
but that's, yeah, I wouldn't want to go.
Well, you have to consider that.
When it had slurs in your
Or like that you're
You know, the I saw this in
Did I do it right?
You need to do it.
Yes.
No, I forgot.
I think I forgot to put mine.
So yeah, just the area is not.
I feel like I got one.
Yeah, exactly.
The sunburn.
Oh, I put it on the thing, that's why.
Where?
And then I'm just gonna really told me was so quiet is this.
No,
I thought she was, oh.
that was
Wait,
wrong.
what?
Cause she had
What's
point,
that,
she had
guys?
0.5, it's 0.05, so.
28,000 per. I don't
And then
understand
you
how
get
that
squares,
was.
so she squared.
Just because.
Oh, then how did you go about doing the
I just did it a different way. So from its original, when is that?
I don't want to do number 5.
That's just 5.
Go, go, you got 1 minute.
Do you have to integrate the number 5? Because I did